we're going to look at a second freefall problem. Just to remind you, we're going to go through all of the same steps: picture with coordinates, a graph, write down a table of our known values, figure out what our target variable is, pick an equation or equations, solve that equation or equations, then plug in our values with their units to get our final answer. So this problem, your cousin is up in a tree. That where they are in the tree is 2.4 meters above you. You have a baseball and you're going to throw the baseball right toward them, not at them, toward them, with an initial velocity of upwards with a speed of 8.22 meters per second. The question is, how long will it take the ball to reach them? So the first thing we're going to do is make a drawing. So I'm not going to try very hard to make a tree, so we'll just do a brown box with, actually is there a pen? Scroll. Okay. Okay, there's a tree, let's make a cousin. So here will be a cousin. There they are on the tree, and we are going to copy and paste you, so that you are down here, and we're going to make a coordinate system. So just like before, we need to come up with the most reasonable coordinate system. Now, there's some ambiguity in the phrasing because I didn't want it to be super awkward. But when something is saying, oh, they're X meters above you, what we're really trying to get at is that the ball will be traveling that distance, right? Unless there's additional information that they're trying to get you to understand about how tall you are and how tall their cousin is and all of that sort of thing, what we're saying is that the ball will go, I'm going to move the cousin a little bit so I can get to the cousin's hand. There we go. So that is going to be the 2.4 meters. So we're going to make that the y-axis like that, and the x-axis like that. Okay. And the reason for this is the ball is leaving your hand here and arriving at your cousin's hand there. And it's important that we do that because when we're solving a freefall problem, we can only solve that problem over the period of time where gravity is the only influence on the ball. While your hand is still moving, gravity is not the only thing affecting the ball, right? While your hand is still touching the ball, gravity is not the only thing affecting the ball. Your hand is as well. But the second you let go of the ball, your hand isn't touching it. So there's no more force from your hand on the ball. Gravity doesn't require contact with the ball in order to exert its force on it. And so the ball is under the influence of only gravity from the moment it leaves your hand all the way up until it touches something else, hopefully your cousin's hand. That's what we're aiming for. With, of course, the caveat that air resistance is hypothetically a factor here, but when you're solving a freefall problem, you've already assumed that air resistance is not going to be a substantial factor, so we are neglecting it. Okay, so here is our problem with a picture and coordinate system. I am going to download this and upload it into our quiz. Okay, so now, very similar to before, we went to draw the set of axes that are going to go with this problem. Now, just like before, we want to draw a set of graphs to go with this problem. Like we said, we're only going to concern ourselves with the interval of time just after the ball has left your fingertips up until the moment just before it actually arrives at your cousin's hand. During that time, gravity is the only thing influencing the ball, and so we know what the acceleration is. It's the acceleration due to gravity. What do we think about the velocity? Well, you gave it some velocity at first, right? That's the remaining factor that was due to your hand. You threw it upward with a positive velocity. Right when you let go, it still has that velocity, but that velocity is decreasing the whole time that it's moving up. Now, in order for it to reach your cousin, this velocity can't become negative, or else it would never have reached your cousin's hand to begin with. It would have turned around and come back down. It could get right to 0, in which case it would have just barely reached your cousin right when it was about to turn around. I'm going to leave it a little high. In terms of grading, without solving an equation, there's no way you could know the difference between it being here and it being here yet. So either of those would be correct. Position. We know that it's moving upward pretty fast. We know that it is slowing down as it continues to move upward. So we want a graph that's going to move upward as time increases. But because it's slowing down, we want the graph to get flatter as it increases. These are the two types of graphs that are increasing. This is the one that's getting flatter. So we'll just put this over here. If you wanted to be very fancy, you could try to make this graph match the velocity graph. And the way to do that in this software is very clunky. Maybe you know a better way to do it. I don't. So you have to hide the end of the graph where it's beginning to level off, and so that this end of the slope is still a little positive, so that it matches the fact that the velocity is still a little positive. Okay, I am going to download this and add it to our quiz. Okay, so once we have the picture with the coordinates and the graphs, now's the time to make our table of known values. So we want a 6x2 grid, and this time we are still moving up in the y direction, and so we are going to have y initial, we are going to have y final, we're going to have v initial in the y direction, we're going to have v initial in the final in the y direction, we're going to have a in the y direction, and we're going to have delta t. So we need to come over here to the Greek letters and insert delta t. And we need to think about which of these values we know. Well, we know that we called our hand 0 for y, and where our cousin's hand is 2.4 meters, and that's where it's starting and where it's ending. So in these cases, we do know the initial and the final positions. how fast is it at the start? Well, we do know that. That's the initial velocity that we gave it. And since it's moving upward, it's a positive value. What about the final velocity? Well, we don't know that. Right? And that's why I wanted to highlight the fact that this is probably a positive number in this case. We don't know that it's reaching the point where it's turning around just as the cousin catches it. There's nothing in this problem that tells us that that should be the case. So this is an unknown value. The acceleration, frankly, in all Freefall problems, unless it's on another planet or something, you should probably know that you know that. And delta t, well, there's nothing in this problem to suggest that we know what that amount of time is, right? That's going to be the duration on our graphs. And so we don't know it yet. But that is the value that we're trying to find. How long does it take the ball to reach your cousin? So let's figure that out. We need to figure out which equation is going to best match the values that we know. And we're looking for time here. Well, this would be good, right? Because we know the initial and the acceleration, and we're looking for delta t, but we don't know what VFX is. We don't know the final velocity. VFY, I guess. Again, y can substitute for all the x's in these equations. You could find VFX by solving this equation as well. Okay. We know the delta y, we know AY, and we know VIY. So if you solved this for VFY and plugged it into the first equation, you would get a solution. But if we look at the second equation, we know YF, we know YI, we know VIY, we're looking for delta t, we know AY, and we're looking for delta t. So this equation only has the one variable that we're looking for. Unfortunately, sometimes it might not be that great to solve because it is a quadratic. It becomes easy to solve if VI is equal to 0 or AX is equal to 0. We don't have either of those this time. But, I mean, you've solved quadratic formulas before in your life, so we're just going to go ahead. We're just going to do this. So, the equation is yi is equal to yf. I know it looks weird, but it'll figure itself out in a second. Plus viy times delta t plus 1/2 times ay times delta t squared. See, it figured out that was supposed to be a subscript. Okay. Now, what we're going to do is we're first going to arrange it in the way we need for a quadratic to be solved. And that means we're going to get everything over to the left-hand side. The way I'm going to do that actually is to subtract the yi over and then just flip the equation around. So the way that's going to look, we're going to put in our equation yf, and that'll fix itself again, don't worry, equals yi plus viy times delta t plus 1/2 times ay times delta t squared. Okay, so we're going to put that closer to the form of the quadratic formula that you're used to, which is to put everything on one side and put it so that we have t squared, then t, and then constants. So that's going to look like 1/2 times ay times, and this is going to be the quadratic term, second order term, delta t squared, plus viy times delta t, plus, and then we're going to get the constant terms over, so that's going to look like vi minus, I said v, yi minus yf is equal to 0. Now, typically I require you to have a final solution before you can plug in numbers, but when you're solving a quadratic, I'm going to let you use a quadratic solver, so you can go ahead and plug in numbers with their units at this stage, and then get the answers from the quadratic solver with a caveat that we'll talk about for a second. But let's go ahead and plug in the numbers with their units, and so we're going to get a negative 4.90 meters per second squared here, and that's going to be times our delta t squared term, and this is going to be our 8.22 meters per second term with our delta t. And then with that, we're also going to have, remember it's yi minus yf, so this is going to be a negative 2.40 meters, and all of that is equal to 0. So notice that in each of these terms, we have units of meters. We have plane meters here, meters per second times time, so the seconds would cancel out, meters per second squared, but the time is squared, so the second squared would cancel out. So now we can use a quadratic solver with negative 4.90 as our term that goes with the square root of 8.22 is the term that goes with the first order, and then the negative 2.4 as the constant term. And let's look at what that means, right? So we can put our numbers into this quadratic solver here. There's plenty that you could use. There's one in your calculator, but there's something I want to show you here. So notice that there are two solutions, right? So the cousin has their first attempt at catching the ball at 0.376 seconds, but if they miss, the ball is just going to keep on going and then come back down, and they have another chance to catch the ball at 1.30 seconds. So in this case, there are two legitimate solutions to this problem. And so you would put as your answer delta t is equal to 1.30 seconds and what's the number? 0.376. 0.376 seconds. And that's it. There's just two of them, right? In some circumstances, you might get two solutions to an equation, but one of them is not physically meaningful. So for example, when you solve a quadratic, sometimes you'll get a negative term and a positive term. That doesn't mean that the negative term is instantly incorrect, but in many cases, the negative delta t means that it would have occurred before the problem started. And maybe that means that it's not reasonable for our specific problem. In a case like what we had up here, we had a positive and a negative. Either of them could have been correct in a general sense, but only one of them was correct for our specific situation. And we had to know based on what we had seen above, what we had already figured out from the graphs.